All right, looks like we can start. Good morning, everybody. Thanks for coming. Morning. In this session, I wanted to cover a little bit of Azure Search, one of the services in the Azure platform. My name is Pablo Castro. I work on the Azure Search team. And my goal for today is to cover both what Azure Search is and also how to integrate it into applications, both mobile and web applications. I'm going to do this as interactively as possible. We'll build a couple of apps. I will encourage everybody to ask questions on the spot as much as I can. I'll just answer them as we go, so we can answer them in context. So thinking about why search, if you look through the applications you run on your phone or you use in your computer, most of apps that have any sort of content, from tweets to documents, to customer relationship management entries, to your contacts, to recipes or restaurants. The way you interact with data that is of reasonable volume as a consumer is usually search first. Bing, Google, and other search engines have shown that we can actually find anything across the whole web using just a quick search. So it's only natural to take that metaphor to applications as well, where data may not be publicly surfaced, so you can actually index with Bing or Google, or it may need to be presented in ways that is not appropriate for a public search engine or for any other reason you want your own local search solution. So Azure Search is the offering in the Azure platform that allows you to create and integrate great search experiences in your applications. So what we want to do today is I have 3 goals. I want to give you a sense of what it takes to get search up and running using Azure Search. I want to talk about some of the specifics of web apps and mobile apps, show you a few things running, give you a few ideas on how to leverage the fact that these are different mediums, they have different interesting things, and also different constraints. And also, I want to talk a little bit about personalization and tuning, how you can use search to create better experiences for your users, and also to drive your business objectives through ranking. So let's start by talking about how do we get search off the ground? How do we start? So typical flow for search is you don't do this in isolation. You usually do it as you're building the rest of your app, but you need to provision some search capacity. You provision a search service. This is true for most of the other Azure services as well. You go to the portal or use APIs for that. Once you have it, you need to create an index and tell us a little bit about what you want to index. Then you need to get data into a thing. And finally, you get to do searches, usually integrated into your application. So let's drill into these steps. And also, how do we think about building the application around these? Very rarely you'll do this in isolation. You'll build an app. You'll have other stores. You have backend components and other pieces that make up a whole thing rather than walking through these as an isolated piece. So let's start by talking about provisioning. The top-level resource that you create when you start working with Azure Search is a search service. Search service is the scope of capacity. So this is when you provision how much search capacity you want in terms of queries per second, in terms of document count, and in terms of storage. And you select a region. So you say in which of all the regions we support you want your data. And sometimes if you need multiple of them, you can define multiple of them across many regions. Services inside have a number of things. They have keys and indexes and data sources and a few other things that we'll discuss later. To provision one of these things, usually during exploratory phases, you go to a portal, and you just do new there. We'll walk through that in a minute. And these things also, like all this functionality is exposed through the Azure Management API. So often for production deployments that need to be repeatable, you use the management APIs to provision search capacity. You can just call them directly or have ARM templates and use the ARM templates to provision maybe search along with a number of other resources you might have as part of your deployment. The search service is also the scope, since it is the scope of capacity, is what you use to manage the elasticity of the service. You can start small, and then as maybe document size increases, or maybe you have a seasonal workload where there is some weeks in the year where you have very, very high queries per second number, and then other times of the year where this thing slows down. So then you can dial the capacity you have on your provisioned on your service to copy or to follow your your capacity needs. So you still continue to get good latency when you need it, but you don't need to pay extra when you don't. So let me switch over real quick, and let's take a quick look at what provisioning looks like in the portal. So I have a provisioned service here, but let me show you what it looks like when you start from scratch. So if you go to the new portal to portal.azure.com, in storage, you'll see that there is a search entry there. So to provision new services, you can go there, pick a name. Let's see if, wow, I took it, excellent. So we offer 2 tiers. There is a free tier, and then there is a paid tier. The free tier is great for experimentation. It allows you to, it has all the same capabilities in terms of functionality as the paid tier, but and there's one in every subscription, but you don't have to pay for it. You can pick, well, usually you pick a resource group, and then you need to pick a subscription where you're using it, and finally you get to pick a location where you want the service located. I'm not sure what's going on with this. So all these decisions are static decisions. Everything else you can change later. But region, resource group, and so on, you'll make it here, and then it'll stick here until you're done with the service. So let me show you one more thing here. Once this wakes up. Hello. I'll come back in a second. So right now we support 8 regions, 4 in the US, 2 in Europe, and 2 in Asia, and we're expanding these. So over time, we'll have better region coverage. So once you have it provisioned, and this will come back in a minute. Let me open another one in the meanwhile. There. Once you have it provisioned, what you get to do is, if it is a free service, then you can manage the rest of the configuration. There's not much to do to the service itself. If it is a standard service, then you get to manage the scale. So in this case, it's a free service. But for managed services, I can get, for standard services, I get to go here and dial up and down the capacity of the service. We surface capacity in 2 dimensions, replicas and partitions, as you can see there. Think of this as there are search units that you can use in 2 ways. You can stack them kind of one next to the other and create more capacity for documents. So each unit takes 15 million documents. And they grow linearly. So if you need 30 million, you get 2. You put 2. If you need 60, you can put 4, and so on. You get between 1 and 12 of those. And then if you need more replicas if you need more queries per second, you can use more replicas for that. So think of replicas effectively as copies of your data. So we may take a little bit longer to write during updates, but during reads, we only need to read from one of them, so we can run robin them. In the end, what you get is this rectangle of replicas times partitions, and that is your total capacity. And this is completely elastic. You can change these at any point, and you can change this online while we're doing reads and writes to your data. If you need high availability, you need at least two replicas to get read availability, and at least 3 if you want write availability. So you get to choose, maybe in a smaller app or in your dev environment, you can say, well, I don't care about availability. I want something that is more affordable. And if I have a big deployment, then I may say, no, I want lots of query per second. And by the way, I also want A-chain reads and writes, so I may want more capacity. So let me switch back here. So great. So once you provisioned a service, you have a starting point, and then either now or later you can tune the kind of the capacity you get for the system. So now that we have a search service in place, next thing that we have to think about is the shape of our index. So each search service can have 1 or more indexes, and think of an index like a table. It's the thing where you put data. And it has many of the elements of a table, like it has a schema, like it has a list of fields, and it has settings that relate to the index, like whether or not course is enabled, what are the various search options that are applied to the index, and so on. And I'll drill into the details of that in a minute. The scheme itself, I'll go through an example immediately after this, but it's pretty usual stuff. There's a list of fields, they have data types, they have names, one of them is a key, and so on. And then they have a bunch of search-specific information. The reason why we have a schema is because when it comes to search, it's not the kind of functionality where we just kind of hold your data, like you give us our data and then we'll give you back. It's more like we need to understand how you expect us to process your information. Like, for example, what attributes of the documents you're giving us do you want us to break apart so we can search on later? Or what attributes you want to do faceting, or which attributes are going to do structure filtering later? That way, we can create the appropriate underlying data structures to do all of these fast. There are also specifics of search that are beyond indexing. There are things like linguistics, and I'll talk more about linguistics in a minute. But when it comes to search, we kind of need to understand specifics of the language of the content, or the languages of the content. And same thing with things like suggesters and scoring profiles, which are very specific to search, and we need to know. So these are things you define in the schema time, and then you use at different points in your application. So let's work on what it looks like to do to define a schema. And we'll explore a couple of options for this. So usually, during the exploratory phase, you often want to do this in the portal, because it's a great way to discover what you can do before you commit to writing a bunch of code. In search, what you can do in the portal, that's odd. Oh, there. So you can create new indexes. And usually the first thing you define is which fields do you want defined in that index. You need to have at least a key field. You can change the name, but you need to have one field that we'll use to identify each one of the documents. And then you can add more fields to the index. So this is the usual stuff. There's basic types. Two interesting types, in addition to the usual suspects like numbers and dates and strings, is we support collection of strings. This is very commonly used in search for things like tags or anything that looks like a structured list of things that you want to collect. And the other one is we have first-class support for geospatial information. I'll talk about this a little more in detail later. But in terms of index definition, you can say that something is a geopoint, and then we'll treat it appropriately. When you define an index, you want to tell us things like, as I mentioned before, like, is this field retrievable? Do you want to do filters on it? Do you want to do facets on it? And let me check a couple of these so I can show you a couple of options. So let's say it's filterable, insertable, and facetable. Let's do everything. You can configure what kind of language you want, and I'll get back to language in a minute. And you can also set up suggesters. So if you want to have autocomplete, you can configure the autocomplete options that you need here. So creating indexes like this is very convenient during exploration, again, because you can create one of these, maybe use Fiddler or any other of these HTTP client tools to explore the functionality and get a sense of what you want to achieve with the search service. Once you're ready to create an app, often you want a more repeatable process, and often you'll just use the API to create the service as well, the index as well, so you can just do it as part of your application deployment. So let me start by doing one of those. So what I'll do is, throughout the rest of the talk, I'll have a couple of applications running in parallel. As you know, or you probably heard, so in Azure, we now have app service as an offering, and app service includes web apps and mobile apps as different ways to support different front ends for your app. And one of the great things that happens as part of this unification is that the backends are very similar. So we get to reuse the same patterns and the same functionality in both the mobile app backend and in the traditional web apps. So I'll do a little bit of back and forth between these so you can see kind of context on both. So let's start with the web app. So let's say that as part of my web application, I want to create indexes if they don't exist already. So on startup, I'll just check everything, and if it's not there, I'm going to create them. So the way you start, like if you're writing your application in .NET, like I'm doing here, the best way to interact with Azure Search is we have a client library that you can find in NuGet repo. So just go grab the NuGet library from there. It'll make your life significantly easier. In other environments, you can just use the REST API or find the right packages for the ones that are available. In this case, I already have the library here. So what I want to do is, first, I want to give myself like an entry point, like a singleton. In a more real application, you probably use like dependency injection framework or something like this and create yourself an entry point for this. I'm going to call this search index client, search client. And what I want to do is, during initialization, check, and if needed, create an index. So let me go grab bunch of code from here, so you don't have to watch me type a whole bunch. So kind of teasing this apart a little bit, what I want to do is first I'm going to create the entry point to the API, which is the search service client. And I'm grab some settings like the service name and the keys from config. Then I'm going to create an index. I'm going to get to indexers in a minute, so let me comment that out. There. And then I want to grab a client specific to that, just kind of scoped to that index, and then publish that as my singleton that I'm going to use in the rest of the app. That way, the rest of my application doesn't need to carry over context and keys or things like that. All of this is captured during initialization, set up as a dependency that you can use a proper injection framework to use later, and you don't have to worry about what are your indexes and so on. That knowledge is confined to the initialization phase. So now let's create an index. I'm going to bring this in, and then I'll walk through it. So what this does is it says, I want to have an index called sessions. That, like if you saw here a minute ago, like I have a couple of other indexes, but we don't have that one yet. So if it's not there, then we want to create a new index. We're going to use the create API. And we're going to pass a bunch of fields. And these correspond to what we saw in the portal a minute ago. And the data set that I have is I took all the sessions from build. And I thought it would be interesting to build something where like you can probably connect to this. Like you have the build session, the build conference, and you have a bunch of sessions, and somebody can come over and say, okay, build the app for build. And one of the pieces that we will all expect is to have good search. So you can see that some of these I set as filterable, some of them are sortable. There is a mix of types and so on. You also see I set up a suggester. So this is a suggester is the building block that you use for autocomplete. You know how you go to Bing or Google, you start typing, and we all kind of wait for a second, see what happens. So it's something that everybody now kind of has been trained to expect. So we provide the building blocks that make it easy for you to build that in your application as well. Great. So now we have, during initialization, what's going to happen is we're going to run this code, and if there's no index, we're going to go ahead and create one. Yes, question? Great question. So the question is, what about schema updates? So we allow you to add fields. We don't allow you to change fields. The reason for that is, like, a search index is an index. Like, it's optimized for retrieval. So changing the options of an existing field usually means reindexing everything. We debate often whether or not we should do the reindexing or you should do the reindexing, and I think we would make people's life easier if we did it, so maybe someday we'll do it, but right now we don't. So if you need to remove a field then, or change an option, then you have to drop the index and recreate it. If you need to add fields, you can add fields at any time. And then they'll just default to null, and then you can add information later. The other thing is these indexes do very well on sparse data. So you can null out things over time if you don't want to drop the index and still just drop information from a column. All right, so I guess this will work much better when we actually call it. So let's do setup search here. Great, so we have an index set up. So let me go here. So now that we have an index, I want to point out one line item here and drill into it a little bit. There is a choice I didn't talk about, which is linguistics, like one of the items in this. Linguistics is an aspect that maybe in other contexts may or may not be important, but in the context of search, we need to understand what's going on. And this is something where we can make very few assumptions. Like I'm sure there's many folks in this room that build applications that don't run only in English or don't run in English at all. Let me kind of double click on this a little bit and look at more details. So if you think about even the most basic functionality of search, the first thing we have to do when we are doing search is break words apart. And that sounds like a piece of cake until you realize there are languages that have no spaces. And then it's not so piece of cake. And then there are some languages, like this happens a little bit in English, but there are, like, for example, Romance languages are heavily inflected languages. That's a fancy way of saying that it's just too many ways to say things. For example, Romance language includes Spanish, French, Italian, and for example in Spanish, the word for go has maybe 50 inflections, 60 inflections, some ridiculous number, and they're very irregular, so it's hard to catch all the forms of it, and they vary with things like gender and tense and combinations of them. So these things are tricky. Even in English, there are things like not all the verbs announced are regular with respect to tense and form. So you have to have awareness of all these details. So in Azure Search, we include support for 50 languages out of the box, where you can just use a default, very general purpose, we call them analyzers, because they do more than just word breaking. They do a number of things with the input, and this is terminology borrowed from Lucene, which is a well-known open source full-text search library. So we offer standard analyzer. It just works, like it uses generic functionality to deal with language, and it does okay. It does pretty well in Western languages, not so much in others. But then we let you choose specific languages. We also surface two sets. We surface the Lucene analyzer set. These are well known in the industry. We surface them as is, so that if you already have investments in the area, or if you know them well and you want them functionality, you can get it. Lucene analyzers also do, many of them, when appropriate for the language, they do stemming. Stemming is a way to get the root, the stem of the word, so a prefix of the word that is the same across variations of the word. For example, when you have variations in number. And it's like in languages like English is really effective. We went and took, when we were working on building search, we were looking around to see how we could get more language coverage. And it turns out that the Office guys know a bunch about this. They have the word grammar backend, and have spellers and things like that for many, many languages. The Bing guys also know a bunch about this, and they have a thing that we went and integrated into search. So this allowed us to, A, have more language coverage, but also give you different options on certain languages, depending on what you want to optimize for. Like one concrete example of this is the Microsoft Analyzer stack does lemmatization for a number of languages instead of stemming. And this is, it's a little bit on the details side, but it actually has an effect on real apps, where sometimes you have a good volume of data and a dense enough vocabulary that people will just find what they're looking for using the words in the data set when they search. But sometimes, either if the data set's small, or if you have what we call recall problems, like you usually don't find the documents you're looking for within the set, then you want to be more aggressive about finding word variations and things like that. And lemmatization is a way to find all word variations understanding the language. So you catch things like variations in tense that are not regular, so you can't play syntax tricks. You need to understand what words we're talking about. There's no obvious choice here. There's no one that is strictly better than the other. These are different. So this is the kind of thing you choose through experimentation. Let me show you a couple of examples to illustrate the difference between these. And first, to show you this, let me first show you what the index that I'm going to use to demonstrate it. So I have this index that is a simplified version of what we're going to use for the rest of the app. That what it does is, this guy does not like me today. So what it does is, I took all the session abstracts and I indexed them 3 times, or in 3 fields. One of them using standard analyzer, not language aware. The other one using the Lucene English analyzer, and a third one using the Microsoft English analyzer. That way we can kind of contrast the two. Let me run the app while we wait for this. And then, so what I did is I wrote the sketchiest ever web page to just try this out. So you're not going to be impressed by the visuals, but let me try a few things. So if I search for something like web, then we'll get a bunch of search results. It's just a wall of text across the board, and there's not a lot of variability to that. But let me pick on something more specific, like, for example, the word find. So you already can see that there is a little bit of variation. And part of it is for things like inflections. And one thing I can do is I'm using highlighters, which is one of the features that we have where you can ask the system, why did we match a particular thing? So if I hover over these things, you can see the pound. You can choose what separator you want to see why did it match a particular document. So for example, this is an instance where the situation can be pretty fragile. If you just say type finds instead of find, then find is even if we don't do this we don't do prefix search by default. But even if we were, finds is not a prefix of find, so you just don't find the stuff. So tiny things like that, variations in number in this case, variations on who you're talking about, will just get in the way of recall. And this may or may not be a problem in some cases. Find has another problem, which is it's an irregular verb. Whoops. So if you want to say found instead of find, even though probably none of these guys say found anywhere, they say find, we still can locate them. So this happens mostly in verbs in most languages, but it happens in nouns sometimes. Like this is a very contrived scenario. It turns out there is one talk that has the word mouse in it. If I say mouse, then I find it everywhere. Here's one thing you can see out of what mechanical stemming does. So mouse is a word that doesn't exist. The stemming algorithms, usually what they do is they chop off the front of the word, sometimes adjust a little bit. So you still find it. And then if you say mice, which is the plural form, then you'll only find it if you do full lemmatization. This is not necessarily a good thing. It's usually good if you have recall problems, but again, it means you'll find a lot of stuff. So sometimes it may just get you a soup of documents, and if you don't have good polarizing ranking, then this is counterproductive. If you have good ranking, then this is good stuff, because you get good recall and at the same time, good ranking to get the output out of it. All right, so that's languages. So now we have an index. We picked languages for some of the columns. We might have left the default for others. And the next step is, how do we get data into the index? There are two main options to get data into the index. You can push data into the index, or you can let us pull into the index. So the first option is so we offer an API. It's the same REST API where you can define indexes and do gets to issue searches. It has an entry point where you can send us batch requests with up to 1,000 line items, like actions in them, where actions can be merge or upload or delete and so on. So you can send them at any time. We'll process them more or less synchronously. It's not a strictly consistent model. So once we acknowledge back to you that we took it, it doesn't mean that you'll read it right away. We may take a few seconds to re-index, because we have to modify. We commit them to the transaction log, but we have to modify the underlying indexes to make it searchable. So it may take a few seconds, and then you'll see it. But you can do this at your cadence, as things happen in your application. Yes, question.
Is there a way to know when data has been indexed?
The question is there a way to know when data has been indexed? No. I guess, yes, you can search for it, but that's you would have to know like a unique thing that, especially if you're modifying an existing record, is particularly tricky, because you have to search for the difference, which is hard to identify. We don't currently provide a way to do this. We thought about providing like tracking values. The challenge with that is that you may, like in the time you turn around from the update and go check if it completed, you may have an interleaved update. So it's unclear, what state are we reflecting. So we haven't done anything about that yet. So when it comes to push indexing, there are a couple of ways you can approach this. One is, as things happen, you can go turn around and update the index. An example of this is maybe your application backend, you get the updates, you push them into the database, and at the same time, you go push them into the index. Or maybe you put them in a queue, and then you have a worker that picks up from the queue and updates the index. The nice thing about that is that changes in the index happen more or less as they're happening in the application. So for things where the user may make a change and immediately turn around and see if the change is there, that's a good pattern, because otherwise people will think the update didn't work or something. So you want to do something where you do it relatively quickly. It also means that since you are calling us, the data can be anywhere. So it has to make it into the index, but we don't care if you got it from some other Azure service, if you got it from an on-premise piece of code that actually, even the indexing code is not running on Azure, it's running on your own servers, or even in some other cloud thing. Like, as long as you manage to call us, we don't care where you're coming from. So it means you can index anything. In terms of patterns, one thing that fits really well here, if you want more of a periodic thing, or if you're polling from a queue, is so web apps, and now thanks to the app service integration story, mobile apps as well, have this thing called web jobs. For those not familiar with web jobs, they're a great way to run arbitrary background code as part of your web application, in addition to the interactive code. So if you want to do indexing with web jobs, what you can do is, in any regular mobile or or a web application, you can go to the app, and then there is a way to add a new web job project. And usually web jobs are simple console apps. They're just deployed in a way that get run in the background. And then you can choose to use the SDK to have more integration with them, or you can just run on your own. A simple example, I have a simple example already created here, where this is all there is to the program. I'm just new in the host and waiting for it. And then I have a simple function where during initialization, I get my own client, and I have a different index here that I already had set up. And then what you can annotate methods with particular triggers, and then the triggers just do a lot of the work for you. In this case, I have this trigger that says, whenever there are new blobs in this Azure Storage blob container, just call me. And here you can use a blob type, and then you get all the information about the blob. Or in the simpler case where it's just some text, you can just have a string, and then they'll just extract the text and then pass the text to the function. This is actually pretty complete. Like if you throw an exception, they'll retry later. They do poison message handling. It's actually a really good solution with very little work. And the awesome thing that it has is it runs locally as well, because it's just a console app. So it's very easy to debug and develop, and then you can deploy it as part of your application. So what we are actually doing here is whenever we get a new blob, then we'll catch the blob, we'll build a batch. In this case, we'll build a one-document batch. When we create a new ID, we take the content, and we make up a new field called date, and then we just call index. And that will just push it to a store. If it succeeds, then a few seconds later, you can search it. And this is, let me show you an example of how this looks like when it runs. This is just Storage Explorer. I have a container here with a couple of blobs. They also keep track of what blobs they already went through and called you for, so you don't have to, you don't redundantly index stuff. So let's create a new blob here, and then set a breakpoint here. So if I run this guy, then on startup, they rescan the thing and detect changes. And then what they do is every few minutes, I think the window it can be up to 10 minutes. So it's not a real-time thing, but it's pretty regular. Then they'll detect changes and then call your function to kind of catch up. The one thing to think about is, in this case, if you have something where occasionally a blob get added, maybe a few a minute or a few an hour, then you can do something like this because the programming model is so clean. Like in fact, here you can see here's the content of the blob. So we'll build a batch, and then we'll call index to index the batch in the client. We didn't get any exceptions, so I'll just hit 5. And if I go here now, if in a few minutes or in a few seconds we check again, statistics are not updated real time, but once they are updated, then here we should see like an extra document here, like a document count of 3, because we push the documents as they happen. I really hope the portal picks it up a little bit. So anyway, so the great thing about push then is you can get data from anywhere. You can push data at your own pace, and you can batch things together. And if you have something like this, if you want to do it regularly, you can use web jobs. If you want to do it reactively, you can inline it with the rest of your app. So how about the other option? What if you don't want to do this work, and you want us to do it for you? So we have this other thing that is called indexers. So indexers are a mechanism that allows us to do the bulk of the work for indexing for you. So the way indexers work is we have a set of specific data sources we support. Right now we support SQL databases on Azure, Azure SQL DB. You can also do it with Azure on VMs if you set up the firewalls right. And we also support document DB out of the box. When you create an indexer, what you do is you point us at the store. You give us a specific data container, like a table or a collection or a view, and then you give us a policy. Policy includes things like how often to check for changes, and how to do change detection and deletion detection. And with that information, we will do everything else. So you can set that up and just fire it off, and then we'll regularly execute this and pull the information. Since indexers and indexes are these separate things, there are a number of interesting scenarios that come out of this. So for example, like the trivial case is you have an index, you have a data source. Let's say you have a document DB database, and you have a collection in it. So you can pull from there and set it up on the index. And then you set it up and forget it. So from time to time, you just go watch it to make sure it's in good shape. And you can monitor it in the portal. But But you can do other combinations. Like, for example, you can have two data sources, two indexers, same index. So like an example of this is maybe you have your data in document DB, so you push from there. But then maybe you have an analytics loop that maybe grabs the logs and things like that, computes interesting signals or tags or does classification for your users. And then you turn around and after all that analysis, put that, say, in a SQL table, and then periodically pull from that SQL table and merge it into the same index. We use merge operations for this. So as long as the keys line up, maybe one of them updates the first 5 columns, and the other one updates the second 2 columns or fields. So this is a way of consolidating multiple data streams into a search same index to construct a whole experience. The opposite also works. You can have multiple indexes with multiple indexers pointed at the same data source. An example of this is, let's say you want multiple search services in multiple regions around the globe, either for redundancy or for latency optimization. What you can do is you can have your primary store in a single place, but then have multiple search services, each one with their indexer, pointing all at the same data store. So they will all follow the changes as they happen in the primary store, and they'll independently populate their own indexes. So there are many ways you can kind of arrange these into a workable scenario. So let me show you how do we set this up, and what does it look like in the portal. So first of all, I mentioned, so if you have, this is a different service that I have, where I had an indexer already set up, and I let it run for a while. So when you have indexers, you can monitor the indexers in the portal. You can see success and failure rate, because these things run in the background. So you need to find a way to know how they're doing. You can monitor them through the API, or you can come to the portal, and then you can see execution times and frequency. And if there are errors, you can go here and see the errors that happened in the last execution or the last few executions. So following the pattern that we had before, let's actually, as part of creating the service, let's create an indexer. So let's stop this guy. I'm going to go here and bring in this piece of code. What this does is it creates 2 pieces. An indexer is set up with there's 3 moving parts. There is the index, and we already have one of those. There is the data source that defines how do we get to the source of the data, and then there is the indexer, which is the policies and the connection point between the source and the index. When you create a data source, the things you say is you give it a name, so we can mention it in the other parts of the system. You give it a type. Today you can say 2 things here. You can say document DB, or you can say Azure SQL. As we add more sources, you'll see them show up here. You can give it a container. In this case, in the context of DocDB, the container is a collection name. In SQL, it could be like a table or a view. The other thing we support is if you don't say anything, we'll just go pull from the table, or in this case, the collection. But you can also give us an arbitrary query, which means you can do things like filter stuff before it makes it to us. Maybe you have a column that says, search ready, yes, no. Or you can transform. Let's say your input, it needs, in the case of DocDB, it may need some flattening. In the case of SQL, you may want to do some denormalization. Often you do this in views, but if you want, you can inline it here and kind of encapsulate the whole thing on the data source definition. We need credentials, of course, and then we need 2 policies. We need to know how to detect that things changed, and we need to know how to detect that things got deleted. For change detection, it depends on the data source. We have, if you're targeting SQL Azure and you're using tables, we can use a change tracking mechanism that is built into SQL that is very efficient. It allows us to track inserts, updates, and deletes as well, and it kind of just works. So it's very convenient for this. The other thing we can do is we can do high watermarks. Both in SQL, you can do row versions, and in document DB, there is a timestamp column _TS. That if you point us at that, then we'll use that as a way to detect when things were new or were modified. And then for deletions, you can give it tombstones. You can give us a field, say, called deleted or something like that. And you can say, when the field has this value, then consider it deleted from the index. And then you can garbage collect them from your original source once you know that we caught up. And finally, the indexer has a name, has a data source, has an index, so it kind of brings all the parts together, and it has a schedule. So in this case, I'm saying every 10 minutes. So great, so we have an index and we have an indexer. Let me update this piece. There. So what we do during initialization then is we create an index, create an indexer, and then don't do this in your app. I'm resetting it here because I did a run before, and I want to make sure I reset the state of the indexer. If you do reset, what that means is forget about your change tracking information and start over. And then I'm forcing it to run here just because if not, we'll have to wait for 5 minutes. This is very convenient during iteration and debugging. You can, in addition to the schedule, you can run the indexer interactively. So at this point, we have enough building blocks that during startup, this application it's not going to do anything interesting on the search side, but it will set up our index and our indexer. So the portal really doesn't like me today, but if it maybe gets into a better mood, let's see if I can show you the index. It'll come. Trust me, there's going to be an index there in a minute. So the other thing I'm going to do, let's see if I open another one. So what I'm doing here is I have a DocumentDB collection. Whoa. That has all the build sessions. So my indexer is going to take that from DocumentDB and push it into the index. So let me quickly show you, go to Document Explorer, and let me show you an example of a document. So this is what a document looks like. It has like a code, and it has a title, it has an abstract, a few tags, speakers, and a start time, room, pretty standard stuff. So now all of that is in the search index. So what we want to do now is actually search for stuff. We have the data in the index. Either we pushed it or we pulled using an indexer, and the next step is to search. So the mechanics of search tend to be pretty simple, because once you manage to get the data in place, then all you need to do is collect search requests and push them into Azure Search. If you don't say anything specific about ranking, and I'll talk about ranking in a minute, then we'll just do default ranking. We'll use the frequencies of the words and things like that to find the most interesting documents, and then return a set of matching docs in ranking order. We support simple primitives like plus and minus to tweak the search a little bit. Think of it as an end-user query options kind of thing, more than a developer. It's not a query language. We have separately from this, we have filters and projections and sorting and so on that is more like not what you would expose to the user, but rather what you use in addition to the user input if you want to filter or sort things. So one interesting choice you have to make when you're searching is, are you going to search from the client or are you going to search from the server? If the data you have needs to be secure and it's not public, then the option is clear. You got to search from the server because you have to hide the keys. You can't access. If you can access from the client, say from the browser or a phone, if you can access the index directly, then everybody else can. In some cases, it turns out that your search index is already exposing all the information in the index. There's nothing internal there. And in that case, you may choose to do it from the client. You save a latency hop, so you save some latency there, and you can do everything like in JavaScript, or in case of the phone, you can do it directly from a phone or a mobile device. The other thing you can think about here is when you render search results, well, you can choose what to pull from the index. And you can also choose to stash things in the index that are not searchable. You can disable everything else. What this allows you to do is you can stash information in the index that you'll use for rendering purposes, even though it's not about search. And this saves you round trips to your primary store. So for example, if in search results you want maybe a picture and some description that you're not searching, you can stash the URL to it in a field in search, project it in during the search results, and then render it in the UI. So you can do full rendering without touching your primary store. It's going to be much faster. So let's very quickly hook up search here. So what I'll do for search is I have this very simple page, and let's bring in a couple of building blocks to it. And I'll walk you through each part that I'm bringing in. So first thing I need is a simple list where we can render results. So let's put this in here. So what I did is, as a model for this view, I'm using Razor, so I get a typed model. As a model for the view, I'm just using what the search primitive in the Azure Search SDK returns, which is a very convenient model. It has the list of all the hits, all the documents, cores, and so on. So all I'm doing here is for each hit, get the title of the talk. Remember, this is the build talks, and then the start time and the room. The other thing that you have to think about is there's a contrast between between you rendering these in big screens versus small screens. Say a mobile app versus a web app. In web apps, you tend to have, especially if you're targeting the desktop, you tend to have a lot more real estate, and you want to use that to make navigation easier. On the phone or other mobile devices here, especially on the phone, you're more restricted, and you usually are better off getting fancier with how you process input rather than trying to get fancy on what you display and make people navigate, because there's just no real estate for that. So let's start with the web version of it. And for the web version of it, where I'm going to assume I have some good real estate, I'm going to do facets. And I'm going to show you what facets are in a minute. So I'm going to do facets. You'll see how all of these comes together in a minute. But I'm going to do facets on speakers, tags, and start time. So now that I have some HTML here, let me bring in the method that will actually do the search. So what I'll do is I'll go to the default controller that doesn't have anything interesting there yet. And what I'll say is I'm going to take a search parameter. And if there is a search in the input, then I'll construct search parameters options where I'll say I want the top 20. I want the total count as well, and also include this filter. Filters usually are not surfaced to the user. I'm doing this here so I can illustrate the point. But these are things like, imagine you have documents that say ready for publishing, yes, no. Or you have the user, and you want to say only the documents that have this username in it. So filters are structured filters, are separate from search, and they're strict. Search is kind of this soft thing, whereas this is like a where clause in a SQL statement. And then what I'm doing is I'm just calling, remember that we stashed out the index client in MVC app. So I'm calling documents.search async. I'm passing the search string that I got from the client, the parameters, and a cancellation token. So let me run this guy. Oh, actually, I forgot a detail. So remember I mentioned facets. So facets are a way of calculating subtotals of things that matched. And this is a very common construct using in search navigation. So what I can do is here I can indicate the list of fields that they need to be enabled for faceting during index definition that I want to facet on for this particular request. I can change this from request to request. I'm going to do speakers, tags, and start time. So let's run this version. All right, so if now I go here and do web, then I get results for web. So what that means is the data made it, so we created an index. The data made it from the document DB store into the Azure Search index. And now we get the search results ranked by relevance. Web is a very general word, so the relevance is kind of a wash. And also, we got all these things have been called in facets. So this is the hit count by category. It's very common in things like e-commerce websites or things like that. And this is a very effective navigation metaphor. Because you can get a sense of, in this case, all the speakers and all the tags, all the start times. You can do, like if we get more specific on the content of these, like I'm going to say like Linux, then we'll get a few less hits, but you can still see like there are a few tags and a few start and end times. If we get even more specific, then you'll see Azure Search. It's at the top because it says Azure Search. This one has it in the description. And then the rest start to rank less and less, probably because they have the word Azure or Search somewhere in their content. In addition to, so let's do Azure Search again. In addition to this, I can, a very common thing is to allow people to drill into these. Like, for example, let's take Vittorio's talk. And when you drill, you get only the ones there. This is a combination of search plus a filter to create this experience where I can drill down on things and then come back up. And then I can do the same. I can see there is 5 that match at this time. There is only 3 at this time. Maybe I'll pick this one, and so on. So this is an example where like the mechanics of wiring up search are just a couple of lines of code, and you just have to have the setup there on the back end to do it. So similar to this, if we want to have autocomplete on these, the mechanics are very similar. So I already indicated which field I want for autocomplete. So what I can do is I can add an entry point to my controller for it, call the suggest API instead of the search API, pass what the input the user passed so far, a few options, like in this case I enabled fuzzy matching, and return this down to the client. In this case, I'm returning it as a JSON array. And this allows me to use jQuery's autocomplete widget. How do you UI depends on your app and what you're doing. In this case, I'm doing something very simple where I'm just doing the default jQuery experience. And let's give it a minute to load. So now, when I start typing, I get suggestions on what is it that I may be looking for. And if I get more specific, then I'll get more specific on the suggestions as well. So this is a way to, these are things people tend to expect in search, and we make sure it's easy to wire them up. All right. So at this point, we got the basics of search in place. I want to highlight some specifics, though. There is a lot in common when you build web and mobile apps, especially if you're using app service, because a lot of the backend is in common. You can use the same controller model. You can use web jobs. You can use the SDK if you're doing this in .NET, and so on. But there are some differences that you want to acknowledge if you're doing targeting one or the other. In web apps, you have a different amount of real estate, and you can depend on the user giving more input in general, because not only you have more space, but input is easier to do. You have mouse, you have keyboard, and so on. Mobile apps are trickier because the input is trickier. Like you want to write less, you have less surface area, less real estate to operate, and so on. So usually, your best bet for input is context. Take as few words as you can, and then use the context for the rest. Sometimes you know who the user is. You know what time is it. You know where the user is. Like if your application asks for all these options when you create it, then you get access to all this context, and you can use this context to make search better without making your end user work. Also, like one kind of line of fine print there, I just demonstrated suggestions. Suggestions in the phone doesn't always work that well. Like usually predictive word input is very effective. And these things are different. So you kind of have to explore which one you want depending on your context. So one option for input is to use voice. Depending on your platform, there's different levels of support for voice. In the case of Windows, we have Cortana, and Cortana has a great extensibility model. And this is a great match with search because in the end, if you think about Cortana, even today in Windows Phone 8.1, there is already an extensibility infrastructure for it, and it gets much better in Windows 10. If you think about interactions with an agent like Cortana, usually you trigger it somehow, and then you say a bunch of words. And that's what you have to work with, a bunch of words. So structured stores are not a natural target for that unless you really restrict the vocabulary of what you can say. If you want to take arbitrary input, then what you're looking for is, what is a thing that I can give it a bunch of words, deal with the realities of language variation, and give me a set of ranked results that then I can present? Well, that is what search does. So there's a very natural kind of integration point between doing voice input, things like Cortana, and doing search. And I have, let me quickly show this working. So I have an example I can show you, and this is based on actually an example we're going to put out there that has just a different data set, so you can pick it up if you're interested. So here's a simple phone app. I have my phone here, so let me project it. There. This is a Windows Phone project. And in my data service, what I have is the same search primitives we were using before. The SDK, same SDK I was using on the server, also runs in Windows apps. So I'm using it to create a couple of search experiences here. One that takes a query, and one that uses the context, in this case, time and who the person is. And then, as part of the Cortana extensibility infrastructure, what you can do is you can define a set of rules that say what are the prefixes that Cortana should react to invoke your application. And once you're in the context of the application, then you can say what patterns you want to recognize. So if we execute this guy, then it'll get deployed to the phone. And there's a couple of things we can do here. Make this a little bigger, and let's give it a second. So one is you can just say, find session and type something. We'll type Azure. And then we'll go find the sessions in the index and then come back. But then we can do other things like, coming next is a very simple way to just give me the sessions that are coming in the next hour. And it's a great way of not having to do a bunch of input. And then if you are registered with Cortana, you can do the Cortana thing. And I'm going to give it one shot. I have this slight accent, so we'll see how that goes. Build, find me sessions about Azure Search. Well, it found nonsense, but it at least invoked the build application. So actually, Cortana, I'm sure the other ones are similar, but the accuracy they have is actually pretty impressive. And they're a great way to do search input. So now you can have an application that you invoke without even it running. You just press and hold for Cortana, then say the word for your app that invokes your app, and then you say a few words, and boom, you have a search. And sometimes the search is no search. You can say things like, build, what's coming next? And that's a query that contains no words of the domain. It's invoking the what's coming next queries, like it's a query by time. So this is a great way to provide an easier experience on mobile devices. The interesting thing about this is that this composes really well with good relevance, because you want minimum input. Like in this case, I just said what's next. So how could we do things like what's next better? So this is, I forgot to mention, so in addition to voice input, location input is just as important. If you know where you are, like in the case of the build example, it's not as compelling, but if you're looking for a trail or a shop or something like that, then geospatial input is just as important. So this is a context where, as I was saying before, in addition to location and time and voice input, having custom ranking can make a huge difference. And there are a few patterns that we see for this. One is just data that is in the files. And we have a thing called scoring profiles that allows you to, it takes a couple of steps to build, so I'm not going to build it here, but so scoring profiles are a way to connect the dots. You can say, for example, things that are happening sooner are more relevant than things that are happening later on. And you can say by how much. And these are based on data in the documents. You can also personalize. We have a thing called tag boosting that what allows you to do is, let's use build to describe this by example. Let's say every session has a set of tags. And then every user has tags. And you can have tags as a user because you picked them, or because using clustering and some machine learning technique, we derived them out of your prior conferences where you rated well or not well and so on. So now we have them. So tag boosting allows you to boost documents where when you pass the search, you pass the tags of the user. And whenever we find a non-empty intersection, we like those documents better. That doesn't mean we're not going to offer documents that don't have the tags. It means that we skew towards the ones that have the tag, all other things being equal. So this is a really powerful way to feel kind of a personalized experience for it. And then finally, you can do analytics, where you can compute signals, like, for example, tags or popularity, and feed that back into the index and use it as input. With all these things combined, next time I pick up my phone and say, what's coming next, it'll do it based on the time, based on the popularity of the session, based on my past history using tag boosting, and it'll give me a very, very kind of custom experience for my specific preferences. And this is what you expect from search. Very, very little input, great, very compelling answers. And so users will be kind of surprised by your application suggesting the right thing in the right context. So just a quick walkthrough of what these things look like. So usually, when you have a full kind of telemetry loop like that, you start by having the original text in something like DocDB. Users generate a bunch of traffic that hit your search index, but you also grab those logs, and you can put them in something like Hadoop. Hadoop in Azure via HD Insight is a very non-threatening thing. I know like it sounds like you had to deploy a whole cluster and so on, but it's actually very straightforward to do because they manage all the deployment. You can even use Azure Data Factory to spin the cluster up and down so you don't have to pay for it all the time. So there's a very, very well thought out story where you can do heavy analytics without becoming an expert on infrastructure and without paying a fortune. And once you have this data, you can feed it back into the index using the double pipeline model that we talked about before and make it increasingly more relevant as your application gets smarter and smarter. So with that, I want to recap. So we provisioned services, created indexes for those services. Then we use pushed or pull models to automatically bring the data or programmatically bring data into the index. We defined a bunch of linguistics options that allows us to have better experiences for the language we're targeting. And then we created UIs and ways to interact with search, both in desktop and mobile devices, including Cortana input to have great search experiences. And then using scoring profiles and things like tag boosting and analytics, we created more relevant experiences for our users by understanding what they need and personalizing results for their particular scenario. So with that, there is a few resources here. I'm going to hang out here for questions, but first I want to say thanks very much for listening, and I'll be here around the rest of the event. Hope you have a great rest of the event, and let me know if you have any questions.